Hey, I'm Akash Joshi. I'm the operations research guru, and today we're going to be talking about optimization using calculus. So, this video is great for those of you in AP Calculus, AP Calc BC, AP Calc AB, Calc 1, Calc 2. Yeah, so let's get started. Okay, so first we're going to look at a problem that tries to maximize or minimize the sum of two squares of the numbers. The sum of two squared numbers. So the problem says find two non-negative numbers whose sum is 50 such that the sum of their squares is as small or large as possible. So this is really two problems. First, we're going to find the two numbers that result in the smallest sum and the two numbers that result in the largest sum. So first, let's look at the solution and I'll walk you through it. Okay, so this represents our sum here of the squares of the two numbers. And because we said that the sum of the two numbers is 50, over here we have the two numbers being added to equal 50. We can rearrange to get this. So let me clarify, x and y are two numbers. We're trying to minimize or maximize this s value, which is the sum of the squares of the two numbers. So it would be convenient if this was all expressed in one variable instead of just x and y. So we can write y equals 50 minus x and plug that into this y squared over here to get 50 minus x squared. And once you expand that expression out, you get this right here. Then we're going to take the derivative because derivative can tell us information about relative maxima and minima. And then we can find the maximum and minimum values of this function over here. So we take the derivative, we get 4x minus 100. We set it equal to 0, and we get x equals 25. From there, we can obtain y equals 25 from plugging it back into this equation, from plugging x back into that equation. And once we get x equals 25 and y equals 25, we get s equals 1250, and this is the minimum value. Okay, so basically went through all these calculations. How do we know that this is the minimum value? So the derivative, when we set the derivative equal to 0, that's going to give us the location of relative values. It can either be a relative maximum or a relative minimum. So how do we know this x equals 25 is a relative minimum? The way we do that is we write this table over here, and s is over here, s prime is over here, and on this x-axis we have values for x. So x can be anywhere between 0 and 50 because we know the sum is 50 and we know that the numbers are non-negative. So when x is 0, we have this over here, and when x is 50, we have this over here. So that's kind of like our domain. And when we have x equals 25 over here, we have this other boundary, which we obtained from over here. And if we plug in a value between 0 and 25 into s prime, so say we plug in 10, 10 is between 0 and 25, we get 40 minus 100, 40 minus 100, which is negative. So s prime is negative, and that means s is going to be decreasing if we graphed it. And then if we plug in a number between 25 and 50, let's say 30, then s prime is going to be positive because we get 120 minus 100, which is 20, which is positive. So if s prime is positive, then we know that it's increasing. And if we graph it out, if a function is decreasing and then suddenly starts to increase, that value must be, this value in the center right here, that value must be a relative minimum. So therefore, at this value, x equals 25 and y equals 25, s is minimized. Okay, so and if that gives us the small answer. So if we're trying to find the two non-negative numbers whose sum is 50 such that the sum is as large as possible, then we're going to try to look where s is maximized, and this is either going to be at one of the uh, domain boundaries or at that value that we obtain when setting the derivative equal to 0. So when we set the derivative equal to 0, we got x equals 25, but that turned out to be a value for which s is minimized. So s is going to be maximized at either x equals 0 or x equals 50. And turns out when you plug in x equals 0 and x equals 50 into this equation for s right here, you obtain s equals 2500 for both x equals 0 and x equals 50. So it turns out that there are two areas where s can be maximized. It can be maximized when x equals 0 or x equals 50. Because when x equals 0, y is just going to be 50, and when x equals 50, y is just going to be 0. So it ends up being the same thing. Okay, so that's the first problem. Let's move on to the next problem. Okay, this one's going to be an area optimization problem. All right, let's look at the problem. Okay, you have 200 feet of fencing to enclose your rectangular backyard. You don't need fencing along your house because you want to be able to enter the backyard. Find the dimensions that will maximize the area. So here's the solution. I'll walk you through it. And here is our diagram, which is usually helpful in optimization problems. So here's our house, and we have a potential backyard over here that we must spread out 200 feet of fencing to maximize the area. It could also be like this. The backyard could also be like this. It just depends on how the area is maximized. So let's write a formula out for the area. Area is x times y, the width times the length. And the sum of two of the lengths plus the width must be 200, since we only have 200 feet of fencing. That's how we get this constraint over here, and we can rearrange that constraint to look like this and plug it into our area formula. So area is going to be equal to 200 minus 2y times y. We get this over here, and then we take the derivative and we set it equal to 0 to find that critical value for which we either will obtain a relative minimum or relative maximum, and we obtain y equals 50. So there's also something called, so instead of doing this chart over here to find out whether our critical value is a relative maximum or minimum, we can also use the second derivative test, which basically takes the derivative of the derivative at this particular point. And it turns out that that derivative of the derivative is negative. And if the derivative of the derivative is negative, then it turns out that this point is going to be a relative maximum for it, assuming that this point makes a prime, or the derivative of a, 0. Okay, so we get a double prime is negative, which means that this is a relative maximum. So y equals 50 is the value for which we will get a relative maximum. So 50 by 100 feet, how I got 100 is I just put 50 back into this equation over here and solve for x. So yeah, 100 by 50 feet are the dimensions that will satisfy the maximum area. It will maximize the area. So 100 is going to be our x value and 50 is going to be our y value. Okay, that's it for part 1 of this video. I will be releasing part 2 shortly with more optimization problems and more problems that are in depth. And once you have watched these 2 videos, you should be good for the optimization portion of the AP Calc exam or the Calc 1 or Calc 2 exams. Thank you for watching.